The definition of a conservative force is that it does not do any work on any closed path. It is a special requirement. Not all forces are conservative. Of all the forces we have discussed so far, only the gravitational force and the force exerted by a spring are potential candidates, as we will show later in the case of the gravitational force. A closed path is a trajectory that returns to its starting point, such as this curve, for example. Let us pick 2 points, A and B, on this trajectory and assume that the object is traveling in a clockwise fashion along this trajectory. We will label the work done by a conservative force while traveling from A to B on the left portion of the trajectory as WA towards B. The work done while traveling back to A from B on the right portion of the trajectory will be labeled as WB towards A. If the force is truly conservative, the sum must be zero. Not only it must be zero with this trajectory in mind, but it must be zero for any closed loop that goes through points A and B. So it must be zero if, for example, the path used to go from A to B is the green straight line instead, keeping the return trip the same. WB towards A does not change value, which means that WA towards B should not change either, so that those two values of work still add up to zero. The consequence of this is an alternate way of characterizing a conservative force, that is, that the work done by a conservative force depends on the initial and final position of an object and not on the path taken to go from the initial position to the final position. It is all very well, but how do you check that the work done by a conservative force while the object is traveling from A to B does not depend on the path taken? I do not want to get into the mathematics of calculus and integration, but I want to give you some hints as to what is involved. Let us take a closed path and create a collection of n subsequent displacements for a trip around the loop. Here is an example where n is equal to 5. The first displacement vector has its tail on the point A and the last as its tip on the point A. Each displacement vector has its tail at the tip of the preceding displacement vector. The set of displacement vectors is such that their sum equals the total displacement, which is 0 since the first vector starts at point A and the last vector ends at point A. You can see from this example with 5 displacement vectors that the figure they make is not following the trajectory very closely. But if you were to increase the number of displacement vectors around the loop, each displacement vector would get shorter and follow the trajectory more closely. With n getting close to infinity, the tiny displacement vectors would become essentially tangential to the trajectory. During such tiny displacements, the parallel component of the force would be approximately constant, and the tiny amount of work done by that force during a displacement delta dj, where j is an integer between 1 and n, would be equal to the product of the parallel component of the force to that of displacement vector j and the magnitude of the tiny displacement delta dj. If the force is conservative, the sum of all these tiny amounts of work is 0. If instead you want to evaluate the work done by the force while the object travels from A to B along the left side of the trajectory, and it takes nb displacement vectors for the tip of the displacement delta d and b to reach the point B, then the work done by the force to go from A to B is the sum of the first nb tiny amounts of work. Let us now zoom in onto one of these tiny vector displacement, delta dj. We want to find an expression for the tiny amount of work the gravitational force does during this displacement. We will use this set of reference directions, where x hat is in the same direction as the horizontal part of the vector delta dj, and the direction of y hat is upward. By creating a right-angled triangle where the magnitude of the vector delta dj is equal to the hypotenuse, we can define the other sides in terms of the magnitude of the components of delta dj. We will limit this discussion to the approximation of a constant gravitational force present in a limited region of space. In other words, in a region where the gravitational field is approximated to be constant in both magnitude and direction. Here is the direction of the gravitational force in comparison to delta dj. Let us break down this vector into a right-angled triangle with sides parallel and perpendicular to the displacement vector. The side parallel to the displacement vector is proportional to the magnitude of the tangential component of the gravitational force. Notice that the parallel part of the gravitational force is in the opposite direction to the direction of the displacement in this drawing. So the parallel component of the gravitational force is negative. Let us define the angle theta as the angle the displacement vector makes with the horizontal. This means that the angle between the horizontal red side and the nearest blue side is complementary to the angle theta. For the same reason, the angle in the blue triangle is complementary to the 90 degrees minus theta, so it is also theta. These two triangles are similar and give us two ways of expressing sine theta, with the ratio of opposite side over hypotenuse. Now, taking into account the sine of delta djy and fg parallel, we can write this equation. This equation is still valid if the y component of the displacement vector had been negative, because the drawing that would go with that situation would show the tangential component of the gravitational force to be positive. Now, isolating for the parallel component of the gravitational force leads to this equation. Remembering that the work is evaluated this way, we can replace Fg parallel with what we found above. Simplifying the magnitude of the displacement out of the equation and replacing the magnitude of the gravitational force with mg leads to this final expression. So we have arrived at this expression for the tiny amount of work done by the gravitational force during the tiny displacement delta dj. Notice that the only element in this expression that has to do with the displacement is the vertical component of the displacement. The horizontal displacement has no bearing on the amount of work done by gravity. The work done on the path from point A to B can be expressed like this, which is the summation of all the tiny amounts of work by the gravitational force during the NB vector displacements, tracing the trajectory from point A to point B. We can first factor out the common minus mg, which leaves the summation of all the vertical components of the displacement inside the brackets. Because of the way the delta dj's were defined, with the tip of one being at the tail of the next one, their sum is the vertical component of the total displacement from point A to point B. The total displacement for this path would be the pink vector in this drawing. The gravitational force does work from A to B only if the total displacement for that path has a vertical component. This is an important result. It means that the only information about the trajectory that is required to evaluate the work done by the gravitational force is the relative positions of point A and B. All trajectories that start at point A and end at point B will lead to the same value for the work done by the gravitational force. This is the definition of a conservative force. Note that if the object returns to point A after going through a closed loop, the total displacement vector would be 0, and so would the work done by the gravitational force. This fits our first definition of a conservative force. There are numerous definitions for the word height. We will not quantify the height of fashion or the height of success, but I want to define the height of an object. Even this one is not that clear-cut. There are at least two different ways of quantifying it. The definition that we will adopt in these series of lectures uses the variable name h, and you can tell from the choice of the variable name that h is a scalar. To define the height of an object, you need to choose an horizontal surface for which points are all having a 0 height. For the entire Earth, the surface would have the shape of a sphere centered on the center of the Earth. If the problem that you are considering is more local in its horizontal extent, then a horizontal plane is a good approximation. The magnitude of the height of an object at location A is the vertical distance from the object to the surface of 0 height. For location above the surface of 0 height, h is positive. It will take negative values when the object is below the 0 level. It has the measurement unit of a distance, so it is measured in meters in the SI system. For example, if we set the surface of 0 height at sea level, the height of a climber at the top of Mount Everest is 8,849 meters, and the height of the wreck of the Titanic is minus 3,700 meters. It is negative because it is below the chosen level of 0 height. Another popular way to describe the height of an object is the vertical dimension of the object. Just think about the dimensions of a box that has a length, a width, and a height. The vertical dimension of an object is actually the magnitude of the change in height between the lowest point of the object and the highest point on the object. It is the magnitude of the change because the vertical dimension of an object is a positive number. According to our first definition of the height, the vertical dimension of an object would be labeled as the absolute value of delta h. The vertical dimension of an object is not a height. It is the magnitude of a change of height. A change of height loses the information about where the 0 height was set. However, recall that the objects in this series of lectures are all approximated to be point-like without shape or volume, so we are not interested in their dimensions. Now let us see how this concept of height is related to the work done by the gravitational force. If an object travels from point A to point B, it will have this total displacement delta d total. The starting height would be hi and the final height hf. It would have gone through this change in height. As you can see from the drawing, the change in height is the same value as the y component of the total displacement, but only if the y components are associated with an upward y hat. This choice for the y hat was used in the discussion about how to estimate the work done by the gravitational force. So delta h can replace delta dty. The advantage of doing so is that h is a scalar, so it is easier to work with than the component of a vector. And by definition, it involves vertical distances, while the value of a y component depends on the choice of the y reference direction. This is probably about time to look at a numerical example that illustrates the preceding discussion. We have a hill of known vertical dimensions. The cart starts at the top of the hill with an initial velocity vi. The givens are the vertical dimension of the hill, the initial speed, and since the roller coaster is frictionless, the work done by friction is zero. The relevant equation here is the change of kinetic energy being equal to the net work. The possible candidates for the forces acting on the object are the gravitational force, the kinetic friction force, and the normal force. The normal force is by definition perpendicular to the surfaces touching, and the displacement is along the surfaces touching. So, the normal force does not do any work. The equation is simplified to this by recalling as well that the work done by the friction is zero. Now is the time to use our expression for the work done by the gravitational force. Since the motion goes from the top to the bottom of the hill, the change in height of the cart is negative. Using the definition of the change of the kinetic energy gives this equation. Quite conveniently, since it was not given, we can simplify the mass on both sides and arrive at this. Isolating for the final speed gives this expression, where only the positive root was kept since we are looking for the magnitude of the final velocity. Let us substitute the givens and arrive at the numerical answer. This is our final answer. This concludes our lecture on the conservative forces. The concept of conservative forces will help define a different type of energy, the potential energy. This will be the topic of the next installment.